Okay, we'll get underway here. We've got a lot to accomplish tonight. I hope you all studied and are prepared. As I mentioned to you last time, we're going to have a quest. I put it up early so that you could get started on it. And it's not like a quiz. It's not like a test. So it's not something where accommodations or anything count. You just have to participate in order to make it happen. So let's do a little bit of a review of a couple SAP 1 facts and figures. Let me find my notepad here. Okay. Alka, why don't you tell me what the name of the 6 T states taken together as a whole on the SAP 1 is called? That's for Alka, specifically directed. Alka, are you there?
Professor, I think some of the students are having trouble hearing you.
Okay. Okay, Andrew, you look like you're at the top of the list now. What's the name of the 6 T states taken as a whole?
Would that be the ring counter?
Well, that's where we keep track of it. Basu, what's the name of it?
Instruction cycle.
Okay, instruction cycle. And Basu, what are the first 3 taken together called? The first 3 T states.
Is it patch cycle?
What cycle?
Patch.
Yeah, the fetch cycle. That's right.
Right.
Brittany, what are the 4, 5, T4, 5, and 6 called, taken together as a whole? Brittany, are you there?
She still can't hear you.
I get that excuse all the time when people get asked questions. Saren?
I'm not sure, Professor.
What's the name of the T4, T5, and T6 taken together?
I don't know.
Dante?
That'd be the execution cycle.
That's correct. It's the execution cycle. Okay, so all 6 T states are involved in executing an instruction. The first 3, all instructions share in common. It's when they fetch, the processor fetches what the instruction is. And finally, the execution cycle may be unique to a particular instruction. In our case, all 5 of our instructions have unique execution cycles. As a matter of fact, one of them doesn't even have an execution cycle. Hermal, what is that one?
Is that output?
Jay, which one? What is it? What is it called?
Output.
Yeah, it's the halt cycle or the halt instruction. It only goes through T3 and really halfway through T3. So our instructions are add, Well, let's start with the first one. Load accumulator, add, subtract, output, and halt. Menotti, what's the opcode for a load accumulator?
Give me 1 second, Professor.
Okay.
Would it just be 0000?
It would be. And what's the address portion of that going to be, Matthew?
The address portion would be, I'm stuck between 1,000 or just all zeros. I think,
Okay, well, it's
or Z's.
four values, which is where you go to get the data you're going to load into the accumulator.
Mhm.
Okay. Mohammed, what's the add instructions opcode?
Oh, it will be 0001. My bad.
Okay. And again, the address portion is simply going to be the address we need. Nicholas, what is the subtract instruction?
0010.
And the cumulative. Okay. We know the out is this, and we don't care what these bets are. We know halt is this, and we don't care what these bets are. Now, on the quest, I've given you a memory dump of what's in memory. On the left-hand side are the address of the bytes. There's 16 bytes of memory in the memory of the SAP1, and each byte is represented by the data that's at that address. So, for example, at address 0, we have the number 15. At address 1, we have that value. At address 2, we have this value. Address 3, address 4, all the way down at the end here, we have 14 and 15, which would be the 16th byte. So let's go through and decode what's in memory at this point. Let me see if I can find my whiteboard. Okay, the first instruction we have, Newmar, what is it? What type of instruction?
You asked for the type of instruction, Professor?
Yeah, what is the instruction? Now, you guys that are sharing the answers in the background, don't do that. Let people answer the questions on their own. Don't let, I know when they wait to answer the question that they didn't know the question, that they're either getting prompted or they're guessing.
Is it the add instruction?
No, it's not. Patricia, what would this instruction be?
Load accumulator, LDA.
Okay, so the first one is load the accumulator. From address 15. So I'm going to represent the number with a pound sign to indicate that it's an address. So it's from, well, we'll just write it out as a single F because it's a hex nibble. Second instruction, Peter, what is that? Peter, we can't hear you. Make sure you have your microphone turned on. It's a computer class after all. Robert, what would it be?
That's going to be subtract address 14.
That's correct. It's going to subtract away from whatever's in the accumulator, whatever is at address 14. Third instruction, Samir.
Would it be input?
Well, it would be if it had an input instruction. We don't have one of those. Sargun, what would this be?
Output.
Okay, it's an output instruction. Output has no parameters, so we don't care what these 4 bits are on this side. Next instruction. Scott?
Halt.
Yeah, halt. And again, we don't care what follows it. The zeros don't matter. Now, we're not going to point at this instruction because it's after the halt and we can only do sequential instructions on the SAP1. We always start at 0. But if we ever did point at this, this would be an output instruction. This would be a halt instruction. This would be an add. This would be a load accumulator. This would be an output. These would all be loads. For example, if we ever pointed at this instruction, it would say load the accumulator from address 15. So the 1 that's at address 15 would be put into the accumulator. So let's go back and look at our program again. Demoulin, what number is located at address 15? Giving me the number in decimal.
Is it 1?
Yeah, it would be. Okay, so we know that this is the actual value is a 1 for this guy. The subtract instruction here, Yan Wen, says use what's at address 14. What's the value in decimal at address 14? This number right here.
I don't know.
Alka? Andrew, what's the number at 14? 3, that's correct. That was a tough one. So what the problem says, if we just deduce what it says, it's going to load the accumulator with the number 1. It's going to subtract a 3 from it and output the answer. So 1 minus 3 means the answer is going to be what? Brittany?
The output for 1 minus 3.
Mm-hmm.
That's going to be -2.
That's right. So the answer to the problem that gets output here will be the number -2. So in the LEDs, we're going to see the number -2. So we know 2 looks like this. We know that the 2's complement of that, which is -2, is going to look like this. So that's the answer we would expect to find on the output LEDs when the computer program hits its halt. Okay, some of you did very well on that, and you're going to reflect it in your participation grade. Now, the next thing we have to be concerned about is we have to be concerned about how do we map this in terms of signals in a way that's going to be able to be digested to show that we actually understand how the SAP1 works. So what we're going to do is you're going to be given an answer sheet. It looks like this. And what you're going to do is you're going to map onto this all of the signals without respect to their positive negativeness. What's on the W bus? Contents of the program counter, the memory address register, the RAM, and this is the RAM internals, the instruction register, the A register, the unit or adder subtractor, the B register, and the output register. For every T state per instruction on both the low clock and the high clock. Now the quest is to complete our program in here. So we know we have 4 instructions. So we'll have one of these boxes for the load, one for the subtract, one for the output, and one for the halt. And we have to go through each half clock and determine what the values will be. Now, since this is a quest, which is not a test or a quiz, rather it's a way of finding out who studied and looking for participation, this will actually, when you do see it for the first time for a grade where the answers matter, it'll be on an exam. And we'll have one for this middle unit of the class, of course. So what we're going to do is we're going to look at our program. Let me see if I can find our program here again. That would not be it. There's a PDF file somewhere on here. It's probably there. And what we're going to do is we're going to go through instruction by instruction. Let's first of all look at what's been pre-filled in for us. When we push the clear button, Saren, what 4 things happen?
I don't know.
Jay?
Does it get cleared?
What? What 4 things get cleared when we push the clear button?
The address?
And when? Peter? Peter, are you there? Scott?
We set the program counter to 0000. We set the current instruction to 0000. the clock goes low and the state goes to T1.
Exactly. Thank you very much. Okay, so we've now encountered our first instruction. It's in memory at this. We're ready. We just released clear. So at that point, we would expect to have on the low clock EP and LM asserted. Enable the program counter to write to the bus, and when the clock ticks, load the memory address register. The bus will contain 4 Z's followed by 4 zeros. The program counter currently contains the 4 zeros as a result of being cleared. We don't know what's in the memory address register. We don't know what RAM it's addressing because we don't know the address. The instruction register has 4 zeros followed by an unknown address portion. And then finally, A, the unit, B, and the output are all unknown to us. Halfway through T1, the clock goes high. At that point, whatever is on the bus in the rightmost bits gets latched. So the zeros here get latched into the memory address register. Since we know what's in memory at 0000, we now know the RAM contains 00001111 at that address. We enter T2. Hermel, what's the only thing that happens in T2?
Everything is set to Z.
Dante, what's the only thing that happens in T2?
We bump up the program counter by 1.
That's exactly right. Thank you for a good answer. So what we're going to do is we're going to set CP, the only signal we need, which tells the programmer to count on the rising clock. That, of course, happens on the low clock. As soon as we do that, the bus goes to all Z's because nobody's driving it. Nobody's enabled. Halfway through that T state, the program counter gets bumped to 1. We enter T3. Remember, the names of our states are the address state, the count state, the X instruction state. Okay, it's all part of the fetch cycle. So in T3, we're going to move what's in the memory into the instruction register. So we need to do chip enable to allow the memory to speak, and load instruction register to allow the instruction register to take the data in on the rising clock. So immediately upon entering T3, because we've told the chip it can write whatever's in memory, which was we saw over here, gets right here, I mean, gets written to the bus. Now, halfway through, the instruction register gets that piece of data and immediately starts broadcasting those 4 zeros down into the controller sequencer, so that as we enter the execution cycle, the controller sequencer and the control matrix know that we're getting ready to execute a load accumulator instruction. Now we enter the execution part of that. What happens during T4? Robert, what's going to happen in T4? What signals are going to be asserted?
Well, we're going to assert the memory register.
Who's going to be talking and who's going to be listening?
Sorry, give me 1 second. The memory array address register is going to be listening.
Okay.
And the instruction register is going to be talking.
Okay, so we'll enable the instruction register. Let me put an X there. And the memory address register is going to be listening. So what's going to appear on the bus at this point? Who knows the answer to that? Scott?
We'll have Z's in the first 4 bits.
That's correct.
Then we'll have the operand in the next 4 bits.
And what is our operand on that first instruction?
It is 1111.
Oops. I'm not any good at typing in Excel. Okay, so that goes on the W bus immediately because we have this guy talking. Now, halfway through T4, the clock goes high. This data gets transferred from the bus to the memory address register, which is the MAR, which is right here. And it happens on the high clock, just actually on the edge between the 0 and the high. So what value is going to be in the memory address register? Raise your hand if you know. Mohammed?
It will be 1111.
Yes. Because we know what the address is, what's the value currently being addressed in RAM? Robert?
It'd be 1.
Well,
So
what's all
7
the
zeros and a 1.
T4 ends, we enter T5. What signals are asserted in T5? Mikkel? Who talks?
So the what's it called? Okay, so the pins that are asserted is CE.
Chip enable is going to talk, so the memory is going to talk. And who's listening?
And LB listens.
Will be the accumulator
Oh, LM.
for a load instruction, so LA. Okay, so those are the 2 signals. Here's the bus. Whatever is in the chip, which I think Robert told us was 7 zeros and a 1, goes on the bus. And halfway through, the clock goes high. Who's going to receive the data? Dante?
Our accumulator.
Right, and it's going to be in the second half of that instruction. Okay, now we've gotten the goal, which was to load that number into the accumulator, so there's nothing to do in T6. However, even though there's no control signals, the bus does not remain containing that. The bus goes back to all Z's. Because nobody's talking. And of course, nothing happens in T6.5 either. And then we're going to be ready to enter T1 of the next instruction. Anybody have any questions about the first instruction? Scott?
Do we want to recognize that the adder subtractor also has a value in it now?
Well, we still don't know what it is. We could just write X's, but yeah, we do know it may have changed. It might not have though, right? It might still be the same value. So we won't indicate it till we know the actual value. But you're right, it did continue doing the addition of A and B, and since we changed A, it's likely that it changed it to a new value. Okay. So let's download. See if I can. Download from the website. Is that it? No. I actually have a bad copy there. That file. So you have a copy of the program. And whoops, that's not it. Well, that actually is it, but we need to put the website in front of it. And yours is going to say XLS here, I'm pretty sure. Let's see if that's it. No. And it will probably download it as a file. And then you can open that in Excel. If you don't have Excel, you can get an open source version of it sometime between now and the next time we meet. Okay, now if you don't have Excel and can't use this sheet of paper, then you can do it just on a piece of paper off to the side or in a notepad somewhere. But you might want to make a note in here of what we added to this thing before we move on to the second instruction. If you've already gotten this and finished this, you can start thinking about what the second instruction is going to look like. The subtract instruction. We're going to move ahead in a second here, so make whatever notes you need, and then we'll continue. Okay, let's move on to the second instruction. As I recall, the second instruction is a subtract. We're going to subtract whatever number is located at 14 here. And 14 has the number 3, as I recall. Sure does. Okay. During T1, what signals are asserted? Raise your hand if you know. Patricia?
EP and LM.
Okay, EP, LM. What is going to be on the bus at this point? Raise your hand if you know. Who now?
Z, 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 Z. I mean, 4 Z's and 4 zeros.
Well, we're in the second instruction. What does the program counter contain in it? It contains a 1 right now. So the 4 Z's are right.
Oh, then 0, 0, 0, 1.
Right. Always going to put whatever the guy that's talking has as his internal contents. Halfway through T1, that gets latched somewhere. Who's going to change in T1? Well, it's got to be whoever is listening, and that's the memory address register, which is the MAR. So halfway through, he's going to pick up the value of 0, 0, 0, 1, which means we know what the data is at that address. It's a 0, 0. Let me see if I can do this with one hand. Not easily. Okay, it's going to be a subtract from address 14, as I recall. We go to T2 low clock. Who wants to tell me about T2 low clock? Minotti?
Is it CP?
Okay, what else changes on that line? Anything? On T2 low clock.
I don't think anything changes. Wait, let me see.
Okay, well, that's the correct answer. T2 high clock, what changes?
It doesn't change.
Tamulin?
The bus is all Z's.
Well, here we did it, yeah, and we didn't mention that, did we? Because I was letting him finish his answer there. But indeed, during T2 low clock, we're going to have 4 Z's followed by the contents of the program counter, which we know to be 0, 0, 0, 1. And it's this value that's going to get latched into the memory address register when the clock goes high. And now we enter T3 low clock. What's going to happen in T3 low clock? Who's going to talk and who's going to listen? Mikkel, who's going to talk?
So the CE and LI are first.
Right, the chip is going to talk. That's CE, the RAM.
Yeah, CE is third, then
And who's listening?
LI.
Right, the instruction register is listening. Let me. And on the bus, that means the chip is talking. We've got to put the data that's known to be in the chip, which was our instruction. And halfway through T3, this gets transferred where? Okay.
To the RAM.
What coming out of this RAM onto the bus, right? So now it's got to be put with the guy that's the load signal. That's the instruction register. So right here, the instruction register is going to get a 0, 0, 1, 0, 1, 1, 1, 0, and broadcast down into the controller sequencer the value 0, 0, 1, 0. So the controller matrix now knows that we're doing a subtract instruction, so it can get ready for T4. We're ready for T4 low clock. What signals are going to be asserted in T4 low clock, Scott?
We're going to assert EI and LM.
Okay, we're going to enable the instruction register. And we're going to load the memory address register. That's so we can get the address portion back over into the REMS domain. So what's on the bus right now? Scott, you can continue answering.
So on the bus right now, we're going to have ZZZZ. And then our operand, which is 1110.
You are absolutely right. Halfway through T4, where does that go? Well, you said we're going to enable the instruction register. So this value is going to wind up in the instruction register, right? No, that's where it came from. We enabled it. We're going to load it into the memory address register. So
Yes.
this guy is going to pick up what address?
1110.
That's right. And what's the data at that address? I wrote a 9 there, but
It is 6 zeros, then 1 at the end.
And because you've been itching to do it, what else do we know? Anything? No, but we know in anticipation that the next step we do is going to allow us to know what's happening inside this adder subtractor. We can't quite figure it out yet because we haven't changed B. But we're ready for T5 now, which is where you've been wanting to get for a while. Because you actually understand this, and I'm proud of you for that. A lot of people, it takes them at least halfway through the second instruction to figure it out. Okay, so what's same? You keep going with me here. What's the control signals in T6 or T5? I'm sorry. Who's talking and who's listening?
It's CE and LB. So the RAM is talking, and the B register is listening.
Okay, and what's going to be on the bus because of that?
It's going to be the data at our memory address. So it's going to be
right here.
Right, yeah, that number there.
And who's going to get that?
The B register. So all the way over to
So
B.
the B register over here, and he's going to get it on the rising clock. And at that exact moment in time, we know this value.
Yeah, so that'll be our 2's complement. It's going to be
No, we don't have, so we didn't turn subtract on. We're doing an addition problem still.
Oh, oops.
So what's going to be here? It's going to be 1 plus 3.
Yeah, so it'll be 0, 0, 0, 0. 0.0100.
Exactly, it's the number 4. Okay, I picked on you long enough there. Now, T6 is entered. Now, this is a little more complicated because we do have the fact that we're going to do that subtract thing happening to us. So let's think about this for a second. In this one here, we've got to take the value that's in the adder subtractor. So we're going to enable the unit, which is this guy right here, third one over. We're going to load it into the accumulator, which is, I think, this guy right here. But we're also going to assert the subtract signal at the same time. Now, what's on the bus at this point? Well, the unit is talking. He's the guy that's enabled. But because of the subtract, this is not really what he contains anymore. What he contains is, because of the subtract signal, he contains the 2's complement of this plus that. So if we take the 2's complement of 3, we get a negative 3. We add a 1 to it, we get a negative 2. Which, if we remember our binary, we have a negative 2. It's that value that makes it out onto the bus. And it's that value that's going to get latched into the accumulator. But what's in the unit is going to change one more time. Because now we're taking this number here and we're adding it to that number there. So what is 3 minus 2?
One.
So we get 1. So the B register has been taken. Now, that isn't exactly what is happening here, right? You think about it. Let me erase those again. This is not what's being added. What's really being added is the 2's complement of this. So the 2's complement of the negative, it becomes a negative 3. So it's a negative 3 plus a negative 2 at that point. Let's do that on a notepad where it's a little easier to see. So the accumulator contained at this point a 1. The B register contained 3. We were adding those up and we got a 4. Now, internally in the unit, we see the subtract signal. So this stays a 1. This gives us the 2's complement of it. And we now add those two values together. And we said that, 1 plus a minus 3 gives us a minus 2. Now what happened was that answer got put into the accumulator. So the answer we have at that point is now in the accumulator. But B still contains this. So we'd have to add those two numbers together. I think I got one too many ones there. And so what's going to happen when we add those? Well, on the right-hand end, we can see those numbers are going to be 1, 1. The next number will be 1 plus 1, which is a 0. Carry the 1, which is going to be 1 plus 1 plus 1. It's carrying 1s all the way along there. So let me... So now we have this number, which is actually the value we're going to see here. So what is this value? Who can tell me what that value is? Just take the 2's complement of it and you'll have the value.
Would that be 7?
Well, let's think about it a second. If we take this number right here and we flip all the bits and add 1 to it, or let's just use the Coakley method here. I'm a 0 key there. We flip everything until we get to the last bit. That's equal 5 in decimal. That kind of makes sense because this is minus 3 and that's minus 2. You'd expect that to be minus 5. So when we get to the thing where we've actually loaded our value into the accumulator, the actual value you'd see inside the unit now is going to be that last number we had there, the minus 5. So 0 is third from the end there. Working in base 3 now all of a sudden. And we have finished with that instruction. However, as soon as we enter T1 of the next instruction, what pertinent signal over here do we remove? Robert?
The subtract.
That's right. We're no longer doing a subtraction problem, which means the number 3 over here, which is still in the B register, is now being added to this. So what's 3 plus a minus 2? Scott?
We'll be back to 1.
Right, so the value actually in the adder subtractor does change. But we don't have to worry about it ever winding up inside of the accumulator because we've already moved it. Most missed questions on the test happen right in that little block of code right there. Now, did I get all my ones and zeros right? I hope I did. If I didn't, you can fix them. But we're in T1 of another instruction. What signals are going to get set in T1? Robert?
Sorry, didn't realize I didn't hit my mic. It's going to be EP and LM.
Okay. EP and LM. What's going to be on the bus? Raise your hand if you know. Mohammed?
That will be 00000011.
Well, the first four, nothing's hooked to them. Robert, what do you think?
It'll be 4 Z's and then 0010.
Okay. Now, that's coming from the program counter, right? He's the guy that put it there. Somewhere along here, I think I put a value in the wrong column. This guy right here, we left out the fact that he's going to that value. Who let me get by with that? Shame on you. Yeah, I wrote it in the wrong place. I wrote the wrong value in the wrong place. Because he was 0 to begin with. He went to 1 here. He went to 2 here. Now we see 2 on the bus. He's going to get picked up halfway through into the memory address register. So we're going to see the value 0010, which means we know what data is there. And the data that are there, if I recall right, is an output instruction. What did I have for the last 4 bits of it? I remember I don't think they were all zeros. What were they, Scott?
1101.
Okay. Now, these 2 values here were pulled off of the bus, but they shouldn't have happened in low part of the clock, right? They should have happened in the high part. So I'm off by 1 row here. And so these guys didn't happen. They happened 1 half clock ahead. Right, because we present the data. It was put on the bus by the program counter. And we know the program counter contains 0010, so it's on the bus. Then halfway through, the memory address register gets the data, which means we now know we're doing a output instruction. During T2, the only signal asserted is CP. The bus goes to all Z's. And then when the clock ticks, this is going to go to the next instruction. And we know what the instruction is at that particular place once we put it in the memory address register. But from here, we just preserve the fact that we know what that is, and we enter T3. On an output instruction, what has to happen during T3? Patricia?
Enable CE and then LI.
Right, we chip enable, and we LI, I think is the next one over. So on the bus, we're going to see the data, which is our instruction. What did we say the last part was? It was 010 or 1101. And that gets latched into the instruction register over here on the rising clock. That's when the clock is a 1. And now we're ready for T4. On the output instruction, what signals are asserted in T4? Dante?
Enable accumulator and load output, EA and LO.
We're going to load the accumulator in previous steps. So LO is EA to put it on the bus. So EA is where? It's right here, this column. And load the output register is the last one. So that means whatever is in the accumulator now will appear on the bus immediately. And the accumulator right now contains 1, 1, 1, 1, 1, 0. Oops, can't type it here. One. I made one little mistake over here. The value here that we're seeing, these two sums, where we actually receive the data correctly on the add, these values are what appear on the bus. Well, there will be a value appearing on the bus perhaps during this cycle right here. Notice we had the 1110. This, the next wrong value, because the bus is still enabled, is actually the only place where we actually see the wrong value appearing on the bus. Saw that over here a second ago. Did I write that? Oh, I actually wrote the wrong value from the accumulator down, didn't I? It's all 1s followed by a 0. So this is on the W bus here. Let's see. I'm going to back up a little bit here. Okay, we loaded the instruction register correctly. Now we're ready for this, which is we want to put what's in the accumulator. And I read the wrong number out. It's this guy right here on the bus. And then halfway through, the unit is going to pick that up. No, I'm sorry, not the unit, the output register, which I believe it's this line right here. Now we enter T6. I'm sorry, T5. What happens during T5 on an output instruction? Dante?
Nothing happens.
Okay, so what actually changes on our picture here?
Doesn't our bus read all Z's?
Yeah, the bus will become all Z's. And it will remain all Z's during T6 as well. Nothing happens, so we have to float the bus, so nothing is presented for anybody. We would then enter the halt instruction. Now the halt is going to be fairly straightforward, right? We're going to assert those two signals in order to get the instruction register, well, not the instruction register, the memory address register loaded from what's in the program counter. So on the bus, we should see 4 Z's followed by the actual value, which is the address of the instruction, which is 0, 0, 1, 1. And that's going to get latched in right here. So what we're going to, well, no, we'll put it in the memory address register. I'm sorry. It's here. What means we know what the data is, and it's a halt instruction. I don't remember what the last 4 bits were. Can somebody tell me? Scott?
All zeros.
Then we're going to enter T2, where CP is asserted. And the only thing that happens during T2 is on the rising clock, this moves up to 1. So it's going to count to the number 4. We enter T3. During T3, 2 signals are asserted. We have to chip enable and we have to load the instruction register, which means the instruction goes out on the bus immediately. And halfway through, the instruction gets loaded into the instruction register, which I believe is this guy over here. Now, immediately this guy starts broadcasting those 4 ones into the controller sequencer. What happens on T4? Robert?
There's no such thing. It
Right.
ended
We
halfway
never
through
get to
T3.
T4 because as soon as the clock ticked and we put this in the instruction register, the controller sequencer saw 4 ones for the instruction, generated not halt, which is hooked to the flip-flops, hooked to the 555 timer, and thereby blocks the clock so that the clock can't do anymore. Now, did I get everything in the right spot? I don't know. I may have missed a box somewhere because I'm, working in a tighter confined space than you might imagine with my screen. So you need to fix anything we got wrong and think about how you will do this when you encounter this on the next exam, because you'll have to, no doubt, do some piece of an SAP 1 program, half clock cycle, and, each bit being accounted for. Dante, you have a question?
You might have explained this already, and I might have just forgotten or not been paying attention. But in the second cycle, the add,
Yeah.
when T2 is on the low clock, why is it 0001 and not all Z's for the bus?
Well, because the program counter always internally contains a number. Okay, so when you're in T2, oh, I see what you're saying. Why isn't this all Z's? This
Yeah,
is
that's what
all
I was.
Z's.
Yeah, I was a bit confused on that, thinking that
Well, I'm glad you asked. Yeah, this is all Z's during T2 all the time.
Okay.
Good shot there. Okay, anybody else see anything that was obviously typed wrong? Are we ready to move ahead? Okay. Let me minimize that. That's a little better there. Okay. I think what we want to do now is start talking about the SAP2, because it's going to be the next thing which we need to get our hands around and get a good grip on. It's a little more like a real CPU in the sense of it has a little richer set of things it can do. But let's talk about the architecture of it. So you'll need to download a file from the website. And I believe I think is what it's called. Why don't you download that and unzip it? And then open up the file which is called sap2.gif, GIF. If we can open that a little easier. And let me know when you've got that and you're, whoa, that's SAP1. I don't want SAP1. I want SAP2. There we go. That's more like it. Okay. Everybody give me a green light so I know you're in your chair. And I know Dante's there. He's just hiding out somewhere. Okay, so let's talk about the architecture of this machine, how it's similar to, how it's different from the SAP1. Now, you want to, as we're going along, rather than writing this down and making notes that you're going to have to look through, learn it as we go. You know, make sure that you're paying attention the whole time and not drifting off and losing track of something. So there are a lot of things that are similar. There are many things that are different. But again, this is just another version of the other. Once you know the SAP1, you know all CPUs, you know all processors. And so this is just kind of a little richer and is going to allow us to explore some more features. So first of all, we're going to talk about the main body of this diagram. And then we're going to come back and talk about the individual boxes. I'm going to omit talking about the top three on the left and this little cluster down on the bottom right initially. I'll come back to them. Don't worry, we will cover them. But they're not exactly as they're pictured, and there's some protocols and things you have to know in order to do input and output. We're going to start at just the general blocks, and I'm going to make some comments before we talk about them in detail. Notice, please, that the boxes do not show their signals. You all have grown up beyond that now, and you should be able to tell me what the signals are for a particular box based on how we've been naming signals and based on what features they have. For example, we see that the memory address register can only read from the bus So we know it will not have an enable signal. It'll have a load and a clock, but it won't have an enable. We notice that the instruction register can only read from the bus, which is different than the instruction register on the SAP2. In the SAP1. In the SAP1, we had a need to be able to write from the instruction register back to the bus in order to take the operand portion of the instruction and get it into the memory address register. We don't need it here because our instructions are not broken up that way. Here we see that we have a register for the B register can read and write from the bus. Our B register couldn't do that. And also our B register used to be attached to the unit. It isn't anymore. Instead, we have a new register called the temp register or the TMP register. We can anticipate that there's going to be an ET instruction or control signal for allowing the temp register to write to the bus. And there's going to be a LT signal available for it to be able to read from the bus. So let's go through and meet our individual boxes and learn a little bit about them. Remember, this is not just to be written down and forgotten, as many of you did on that other computer. You need to keep this in your head and moving around at least until we get over an exam on this. You can't afford to keep diving into notes. You have to know how it works. First of all, notice the W bus is 16 bits wide. Not 8, not 4, but 16 bits wide. Notice that the program counter is 16 bits wide. It can read and it can write from the bus. That tells us a couple things. One, that since the program counter can point at 2 to the 16th bytes of memory, this computer must have 64K or 2 to the 16th, which is 65,536 bytes of memory. So it's a bigger computer. We also can change the data that's in the program counter, which means this computer is going to be able to support go-to instructions, because we're going to be able to execute instructions that are not sequential. And we pick that all up from being able to look at the type of control signals necessary to do it. We'll have an EP, which enables the program counter to write to the bus, but we'll also have an LP, which allows it to load from the W bus. The memory address register can take a 16-bit address in, and notice that it can address our memory here with 16 bits. You'll also, if you look at this closely, you'll see it says it has 64K of memory. 64K means 2 to the 16th. We know what 2 to the 16th is. It's 65,536 bytes of memory. Notice also that the memory is no longer directly connected to the bus. Instead, on a back bus, it's connected bidirectionally to something called the MDR, the Memory Data Register. Notice that it can pass 8 bits of data back and forth between memory and the MDR, as well as 8 bits of memory to and from the bus. When it writes 8 bits of data to the bus, it's always in the right-hand 8 bits. Very similar to how addresses and things were written on the other machine, but in this case, the data itself, the physical data that's at a particular address, is passed on the bus in the right 8 bits. The other left 8 bits would be Z's. Notice that data can be brought in from the bus and can be written to the memory, which means this computer can change the data in memory. Unlike the SAP1, which had the read-only memory. The memory here is readable and writable. There are some signals which we haven't seen that allow us to change whether this is reading or writing to or from the memory data register. And of course, there'll be signals enable, which says put what's in the memory data register on the bus, and load memory data register, which would be LD. We use LD for this because M was used up here. And ED for enable the data register. The instruction register can take 8 bits of data in, and notice that it broadcasts all 8 bits of data to the controller sequencer, who generates the control word. And we, of course, can figure out how big it is because we can figure out what all the signals have to be. The accumulator is the same as our old A register. However, this is not. Instead of being an adder subtractor, this is now a box called an arithmetic logic unit, or an ALU. It can do different logic instructions like ands and ors and zors, as well as adds and subtracts. It's always doing whatever the currently selected logic function is between the accumulator and the temp register. So the result in here is always known if you know what's in the accumulator and what's in the temp register, and you know which logic function has been selected. We also have the ability to produce what are called flags. We can produce 2 flags, one of which is the left bit of the 8 bits turned on? It's called the sign bit. And the other is the entire value that we're using a 0? Meaning that if is the result we created here, is it a 0? Now there's 2 exceptions to that, but we'll talk about them later. Now, not all instructions set the flags. Some do, some don't. But if they do, you can check to see whether or not the number is negative that set the flag, because that means its leftmost bit must be turned on. Uses 2's complement notation. Or we can test to see if the number we produced was all zeros, meaning that all the bits in the register were a 0. We'll talk about the details of that later. We also have 2 spare registers, a B register and a C register. We can use for anything where we need to save data in a place that's faster than regular memory. So we'll start by studying those before we come back and talk about the input-output instructions. What we need to do next is we need to look at the instruction set and talk about how they're encoded and the data that's there. So if you go back into that SAP2.zip file, you'll find in there also a file called inst.gif, which stands for instruction.gif. And we'll go through the instructions so that you know what they are. Notice there's more than 5 here, so you can actually do some real work with this computer. There are a couple things that's missing that make it from being extremely useful, but this is an extremely good job interview computer to show people and ask them to explain things about a microcontroller. It involves enough stuff that you've gotten past the SAP 1 stage of the aha moment to actually being able to apply it to a processor that could actually do something. So we'll go through each of these instructions one at a time, and I'll skip some and then come back to them as we go. I want to point out the various columns we have. This is the opcode and the operand for the particular instruction, as you would write it if you're using an assembler. An assembler knows how to take one of these codes and turn it into machine code. The machine code would consist of an opcode plus some operands encoded in hex. The opcode for each of these is listed next. You would always have this and this available to you if you were doing a problem involving the SAP2, but you might not have anything else. Like you might not have your notes. So you want to make sure you've absorbed how this works with this in order to apply one to the other. Now, not all instructions on this machine take the same number of t-states. So for a particular instruction, for example, add B to the accumulator, only takes 4 t-states, whereas a call takes 18 t-states. And some of the conditional instructions take either 10 or 7, depending what you took the jump or you didn't take the jump. Now, when this instruction completes, the sign and the Z flag will be set. The sign flag will be set to match the leftmost bit of the accumulator, and the 0 flag will be turned on if and only if the accumulator is all zeros. Finally, we have the mode, and we're going to say that this is a register mode, meaning both operands are in a register. Finally, the instruction takes 1 byte of memory in order to encode it. So let's take some of these that we have. I'm going to jump around a little bit as we go here. Add B, add C. What they both say is take the register's contents and add it to the contents of the accumulator and put the answer in the accumulator. So this would take whatever's in B, add it to whatever's in A, the answer will wind up in A. Now you can imagine what registers have to be manipulated over here to make that happen. What signals would have to happen during the 4 t-states that cause it to occur. Add B and add C, very similar. Additionally to those, we have 2 subtract instructions. Subtract B from the A register, subtract C from the A register. Answer winds up in the A register. Notice the one that's shown here is the register that's going to be subtracted away. So it's the second number, the A minus B, with the answer put in the A register. So all 4 of those will be similar, different opcodes, but they all take 4 t-states. They set the sign and the Z flag. They're both register-to-register operations, and they take 1 t-state. Now, similarly to those, we have 2 instructions for each of AND or XOR. So we can do those 3 logical functions where the answer winds up in the accumulator. It uses the register as the one we have listed as the second operand, and the answer goes in the accumulator. Again, they're all 4 bits, or 4 t-states. Set the sign and Z flag, register to register, and they're 1 byte to encode them. Now, additionally, for all 3 of the AND, the OR, and the XOR, we have one that's called an immediate instruction. In this case, the answer will still wind up in the accumulator, but the byte we're going to use is physically inside the instruction. So the instruction is going to take 2 bytes now to execute. It'll take more t-states. It'll take 7 t-states because we have to do more to get it out of the memory. It will continue to set the S and the Z flag, and the answer will wind up in the accumulator. Notice the I in this. Notice also it's called immediate mode. Immediate means the data is immediately available in the instruction. It's not like in some random place in memory. It's immediately in the instruction. Now, to complement these instructions we also have decrement the accumulator, decrement the B register, decrement the C register, increment the A register, increment the B register, increment the C register. Adding one and taking one away from a register is such a common operation that they made an instruction specifically for it. Now, these are a little bit odd. I told you earlier there's a couple odd instructions. The reason they're odd, not the fact that each of them take 4 T states. They take 1 byte of memory to encode. They're register to register. However, the difference in these is that the answer winds up in the named register. If you say decrement B, the answer winds up in B. Decrement C, the answer winds up in C. Increment, where's increment? Increment B, answer in B. Increment C, answer in C. No surprises with increment A or decrement A, it winds up in the accumulator. But that also means that the flags are set not based on the accumulator, but on the result of the operation over here. So if I increment B and it makes a 0 in B, the 0 flag gets set. So that's a little odd. Same thing with C. Okay, now, some other interesting instructions we have that we should look at are these set of move instructions. Notice that we have every combination of register here. They move the value from right to left. So the top instruction here says, take what's in B and make a copy of it in A. Here's one. Take what's in C, make a copy of it in A. Notice that move doesn't mean move, it means copy. So this guy down here, for example, says take whatever's in A and make a copy of it and put it in C. When you're done, both A and C contain the same value. It goes from right to left. They're all 4 T states because they're very fast instructions. They do not set the flags. They're register to register operations, and they take 1 byte of memory to encode. To go along to complement them, there's some move immediates where the data is actually physically in the instruction. So we'd expect the instruction to take slightly longer. It would be an immediate mode instruction. And because the byte is actually physically in the instruction, it'll take 2 bytes to encode it. Now I'm going to pick up some that are a little bit specific. CMA stands for complement the accumulator. Hello, accumulator, nice shoes. No, by complement here, it means take the ones complement. It just flips all the bits in the accumulator. 4 T states, no flags. It's called implied because there is no operand. It's implied because A is here, meaning it's just complement the accumulator. Takes 1 byte to encode it. The halt instruction. 76 trombones, you can remember it that way. The opcode is 76. Takes 5 T states. That's where it encounters, oh, it's been recognized, and so it doesn't go any further. Doesn't set any flags. Has no operands, doesn't even get that far, so we just say it's no addressing mode at all. And takes 1 byte to encode it, the 76. No op, no operation. If we encode 1 byte of 0, if the program counter gets to it, it does nothing. Takes 4 T states to do nothing, so you could use it for timing. If you want to delay for 4 T states. Doesn't set the flags, has no addressing mode, and it'll fit in 1 byte. Two instructions here that are a little unusual for this. These are rotate the accumulator left, rotate the accumulator right. Now let me draw you a picture of that. Use Notepad. If the accumulator currently contains the value that, and we say rotate the accumulator right, it'll do that. We say take the same value I just wrote and rotate it left, it would go back to there. If it looked like this, and I said rotate it left, it would look like that. Think of it as being circular, and it goes around to the left and comes in the right end. If we had a number that looked like this, and they said rotate right, it would look like that when we're done. So it simply takes all the bits, moves them 1 position left or right, and the bit that dropped out is stuffed in the other end. It's called a rotate instruction. Later in some of the instruction sets, we'll have something called a shift, where the extra bit is treated differently. But this machine rotates it, either left or right. Very simple instruction. Takes 4 T states, no flags, implied addressing because it uses the accumulator. Takes 1 bit or 1 byte to encode. Now, the only 2 instructions that can physically use memory in terms of getting memory into the machine are load the accumulator from some 4-byte address or store the accumulator at some 4-byte, or not 4-byte, 4 nibble address. This is a 16-bit address, so it could address all the bits of memory we have. You see down here, store. It's expensive. What's 32 is the hex code, but it takes 13 T states. No flags. It's called direct addressing because we're directly addressing memory bytes. And it takes 3 bytes of memory in order to encode it. The address is physically encoded in memory in Little Endian. We'll talk about that when we encode one. So there's a store and there's a load. So the only way to get things out of memory are to use either the store or the load instruction to get them into the accumulator. And remember, the ones that use immediate instructions are using memory, but the data is physically in the instruction, so it's not the same as being at an arbitrary memory address. Now, the other interesting instructions we have in here are this set in the middle. We have a jump to some address if minus. We have a jump if not 0 to some address. That says jump if the 0 flag is not set. We have a jump if 0 to some address. Again, the addresses would be specified in Little Endian in hex. And these are conditional. Each of them take 10 if we take the jump, 7 if we don't. And we'll talk about how they actually do that kind of later. 3 bytes to encode their immediate data, don't set the flags. We can test to see if that sign bit in the flags is set and do something conditionally. If it's set, we can do something, go somewhere. If not, we just fall through to the next instruction. These 2 test whether the 0 flag is set or not set and do the same thing. Let us continue forward or jump to some other place. We also have one, a JMP, which is jump unconditionally. That's like the go-to. Go somewhere unconditionally. Now we have one that corresponds to that called call. Call does something a little differently though. Call saves the address of the instruction right after the call, and it'll let you return to it later if you ever specify a return instruction. So call and return go together. On this machine, you cannot nest calls, meaning you can't call somewhere while you're calling somebody. We'll do that a lot in high-level languages and in other level assemblers, but for this particular machine, it only lets you do one level of calls. Now, it turns out that the address FFFE and FFFF are used to save the return address when the call happens. And we'll see how that happens when we're talking about it. But these 2 bytes of memory are used to save the return. When you say return, the place you're going to go back to that was sitting right after the call instruction. These 2 bytes of memory are the address of the return address, and they are in Little Endian. Not the address of the return address, they are the return address in Little Endian. The only other address, well, there's 2 other addresses we'd want to know about. One is all programs on the SAP1 after reset begin at the address hex 4 zeros. That's 16 bits. We'll normally be dealing in hexadecimal here. The only other place is that the addresses from 000 to 7FFF are ROM. And the addresses from 8000 up to FFFF are RAM. So although we can write in memory, the only places where it'll really happen is if we're writing at addresses greater than 8000. And we just kind of need to remember that because we write them at lower addresses, they simply won't get saved because you can't write. You could write to ROM, but it won't save the number. Now I skipped 2 instructions in here, the in and the out, wherever it is. And we'll come back to them at a later time. I'll point out to you that they're direct addresses, but the address here is not memory addresses. They're what are called input-output addresses. They each take 10 T-states. They don't affect the flags. And I'll have to show you how our input-output is configured, because depending on how it's configured is how on a particular machine it would behave. So what we want to do is something simple. What we want to do is we want to explore the instruction set for a second, keeping in mind that it's going to be architected on top of this machine. Let's write an example of a program which can add the number 2 to the number 3. And why don't you just jot down how you think that program could be written? And there's 2 reasonably good approaches to it that we could use given what I've told you about the instruction set. So what you want to do in order to do it is you want to write it down using the operation codes. So for example, if I wanted to, let's say I was going to decrement some value, I would say DCR, and then I'd pick either A, B, or C. I'd put it over here. And that would say I'm decrementing what's in the accumulator. And then if the next thing I wanted to do was increment what was in the B register, I'd write it down like that. We will later on decode it. Because these are instructions, there'll always be white space in front of them. We'll reserve the white space for labels. One of the things I could do is I could, for example, I could code at address 8000, I want to put the number 2. So what I'd have to do here is I'd use what are called assembler directives. I would put an org instruction, then I put a #8000. Then I might put the number, which I could call it first. I could assign a byte, another directive, put the number 02 there. That's the number 2 in hex. I could then put the second value, define a byte. That could be the number 3. Now, normally, if I was assembling this, I would line everything up really neatly. And then somewhere at the beginning of my program, you know, I might have a label here which says start. And then I put my first instruction. And I put my second instruction. Eventually, I'd have an instruction down here where I'd put a halt. Now, at the very end of my program, I'd have a directive that said end. And I'd say, where do I want my program to start? Well, I want it to start at the starting label. Now, you might say, well, I didn't ever see these things before. And I just said, no, you didn't. I also called them assembler directives. They do not generate any code by themselves. Instead, they give instructions to the assembler saying that the next things you see need to be at 8,000. So this will be at 8,000. This will be at 8,001. And this says define a byte of data. Well, a byte is 8 bits, 2 hex nibbles. At the end, I'm telling you there's going to be an end statement that says you've seen all the assembly and directives. Have the beginning statement be at start in case our program didn't begin at the beginning. This machine only knows how to do that. So I would put my label at the very beginning, and then I'd put my first instruction immediately after. So anybody have an idea of what instructions I might use in order to make this happen? Okay, well, let's talk about a strategy first. First strategy would be, we need to get the number 2 out of memory into a register. What instruction will let us do that? Scott?
Load accumulator.
So I can do a load accumulator from first. Now, my second strategy is I need to get a number out of memory also into a register. But if I load it into the accumulator, it'll wipe out first. So what could I do? Robert?
You're going to move A to B.
Do I have an instruction that'll do that?
Yeah, move A, B.
You sure? Moving from right to left.
Oh, no, sorry, move BA.
Oh, okay. So you're really moving from A to B. Now, I have the same number. The number 2 is in both A and B. What am I going to do next? Somebody else put your hand up. We got to get it out of memory, right? So Dante, how do I get to get that 3 out of memory?
We're going to load accumulator second. So LDA second.
Okay, now do I need to move it to the B register also?
No, we don't. We can just do...
Okay, what would be the next thing I need to do? Patricia?
Add B.
I put in add B, that's going to take B and add it to the accumulator. And now we don't know how to do an output instruction, but that would be the next thing we would do. So we'll just stick to the fact we now have the right answer in B. Did we solve our problem? Add the number 2 to the number 3? Sure did. Did a mighty fine solution of that. You guys did really well with that. Now what we would need to do is, I'm going to push all this over about 8 positions. Okay, where in memory does this instruction live? Physical address. I told you earlier where all programs begin. Scott?
0000.
Okay, so I'm going to write over here on the left. 0000. How many bytes does it take? Well, we look up load accumulator. Go over to the right, it says there's 3 bytes. So what are those 3 bytes? Well, what's the opcode for a load accumulator? Scott?
3A.
Okay. And then what is the address of first? Scott?
8000.
It's 8000, and we write it in Little Indian. It's part of this instruction. So what's the address of the next instruction, Robert?
0001.
I'm not so sure about that. That's where this byte is.
Oh, would it be 0081? No,
that's way down
that's
here.
where a second is.
Anybody want to help him out? Scott?
It's 0100.
No, we've used up 0000, 0001, 0002. What would be next, counting wise? Give you a clue. Oops, that's much of a clue. 0000, 0001, 0002 is gone, so this is the 3rd byte, really 4th byte, right? We got to put a move A to B. So what is the opcode for this particular guy, and how many bytes does he take? Jamal?
Of 47 and 1 byte.
Okay, he's a 4-7, takes up 1 byte. So what's the address of the next instruction? Scott?
In Little Indian, it'll be 0180.
No, we want everything to be in just hex. Remember, we're accounting for 16 bits here. Took up 1 byte, so that means it took up 3, so 4 must be next. Okay, well, we can cheat and look up here and see. We know what the next opcode is going to be because it's a load accumulator. What address is 2nd located at? Well, if this is a 8000, let's write the numbers next to them here. The next guy, and it took 1 byte. The next guy must be at 8001. So we have to encode 8001 here because it's 2nd we're moving. Now we have the add B instruction. What address is that going to be located at? This guy took up 4, 5, and 6. Come out.
0007.
Yep. And what's his opcode? Patricia?
80 and 1 byte.
80, 1 byte, right? We got one more instruction. What's its address? Scott, what's its address?
0008.
Yep. And we said 76 trombone, so we don't even have to look that one up. And this, we actually have to encode the bytes here. I should write it out the way it would look. There'd be an 02 here, right? And there'd be an 03 here. Oh. I don't know what I'm doing there. I'm just hitting keys like crazy. So this is what the machine would see. Machine is going to see its zeros, 3A0080, 47, 3A018. So typical exam question. Would be to give you this and ask you what instructions are in there and what does it do, which you would decode to this, which you then, using your sheet, decode to this, read the code, and know what it did. Assembler is fun. Just think of that as something fun. So this is for the assembler over here. After we run it through the assembler, this gets generated. This is the actual, it looks more like this. It's a big stream of data. And this is for humans to read and program. This is for us to enjoy knowing how it's encoded. We use our cheat sheet here to figure out what's going on. Now, a second way, let's encode our thing. Let's say that somebody said to us, your program takes too long to execute. How would we figure out how long it takes? Any idea for that? Scott, what do you think?
Count the number of T states.
Okay, so how many does an LDA take?
That'll take 13.
Okay, so there's 13, whoops, not 31, 13 there, and there's 13 down here. How long does a move take? 4? Something like that?
4, yep.
And an add takes 4, I'm sure.
Yep.
What's a halt? 5?
5.
Okay, so we add these up. 26 plus 8 is what, 34? 39. Okay, so let's remember that for later. Take 39 T states. This machine, after the crystal, runs at 1 megahertz. So how long does 1 T state take? Robert?
Be T state is going to be 1/2 of a tau.
I'm looking for a simpler number than that. We know that the clock is running at 1 megahertz. So how do we write 1/millionth of a second? Scott?
Just be 1 microsecond.
Yeah, absolutely. So how many microseconds does our program take? Well, it'd be 39 microseconds. We said there was 39 T states. So now we could do the timing on a different variation of this and see if it takes less or more. So let's write it, and this time instead of using the loads, let's use some move immediates to get them into the registers. And let's see if we can make it run a little faster. So try to write that out. And once you've got some code, I'll get us a framework here. So we're going to have ourselves a start, some instructions, eventually a halt. If we have any data, I'll just call the data this time with a label of data. It's got to be somewhere. Eventually, we're going to have an end, and we'll end with start because that's where it would begin again. So to get data at the right spot, we'd have to have an org to push the data down to that address. So we could say org pound 8000. And so our code is going to go in here, and any data we need will go down here if we have any data we need. So anybody want to take a shot at it? Okay, well, let's do it one instruction at a time. What would be a good first instruction for us to use here? Robert?
MVI A03.
Okay. Anybody want to opt for a second instruction other than Robert? Emma?
MVI B02.
Liking it, okay. Anybody else besides those two wanted to do a third instruction here? Scott?
Add B.
And halt. How many T states does a move immediate take? Scott?
7.
We got a couple 7s here. We got a 4 here. I believe we said we had a 5 here. 9 plus 14, what is that? 23. So this guy takes 23 T states, which is how many microseconds? I can get this one. How many, Scott?
23 microseconds.
Yeah, excellent. Okay, so this is indeed faster. We also use less memory because we didn't have to store anything in the data section down here. Let's turn this into code. So let's push everything over so we got some place to write it. What is jumping over there so far? Okay, what's the move immediate opcode? Move immediate A. Patricia?
3E.
So we got add address 0. We have a 3E, and now we need the data part, which is the O2. Now we got another move immediate, but it's a different opcode this time. And what address are we going to put it at? I think I put that in the wrong line. What's the address for the next one? Matthew?
0003.
No. We have a 0 here. We have a 1 there. So this must be a 2.
Of 2.
Okay.
Yep.
And what are we going to put there for an opcode, somebody? Robert?
Be 0602, and also the first one should be
I thought,
3E03.
yeah, we did those in reverse order from the original problem. And the add, what address is this going to be located at? Somebody other than Robert? Some of you aren't participating at all. Scott?
0004.
Okay. And what would be the add B opcode? Patricia?
80.
Okay, and then we have one more to go. At what the next address where the halt will be? What's the address of this? Robert?
Zero 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 five.
And we know it's a 76. Okay, and this would be the code that would be generated by this particular assembly program over here. And here's some timings and things. So we've got a lot done by being able to do that working with our sheet here. Now, let's go back to the architectural diagram again. If I can find it. This guy. I want to talk about the input-output features of this particular processor. Now we'll scroll down to that to look at it in a minute. If I can get up to that corner. Now, first thing we're going to do up here is we're going to mark out the serial in. It doesn't exist. Actually, let me see if I can open this in Paint. Yeah. Scratch out the serial in. Our machine does not have that feature installed. Down at the bottom, scratch out the serial out. We don't have that feature installed. Now, while we're here, output port 3 works just like the one did on the SAP1. Basically, you put 8 bits in it. It shows you the 8 bits. We bought the low-grade one. We bought the one that's in binary, not hexadecimal. So it's a binary display. But basically works exactly the same as the SAP1. Now, we have a keypad. The keypad has hexadecimal keys on it. We can type, if you picture a little keypad sitting up here. It has a 4x4 keypad, 0, 1, 2, 3, all the way up to F. Now, when you initially start the machine, the keypad is enabled. The moment you type a single key, The data you typed is transferred into this input port here by way of this back bus. The keypad is locked, so you can't type any other keys. And then this ready signal comes on in this port right here. This port is on the right-hand bit. You imagine 8 bits. It's on the right-hand bit, and there's a signal. If it's a 0, it's not ready. If it's a 1, it's ready. So I type a key. The keypad becomes locked. The data is transferred into this port. And after all that happens, the ready bit comes on. So if I want to read the keypad, I first have to determine whether or not it's ready. Ready means that there's a byte for me to read inside here. So I would check to see whether that bit is turned on in code. If it is turned on, it's safe to read one time the contents of the input port. When I read from the input port, the answer winds up in the accumulator. Same thing here. When I'm reading the ready bit, the answer winds up in the accumulator. But I can read only one time. Keypad remains locked. Now, assuming I want one more character or more, what I have to do is I have to do a handshake with the keypad. I basically have to go down to this output port right here, and I have to write a 1 to this acknowledge bit right here. Now, when I write the acknowledge bit, the system pulses it on and then off, which means this pin right here on the hexadecimal encoder sees a signal go on and then off. The moment it sees that go on and off, it resets the ready bit and then unlocks the keypad so that a user could type another key. Now, if we didn't do it that way, and a person saw the ready bit and they read a byte of data and they came back and looked to see if it was still on, it would still be on and they'd think they saw another character. And they just keep reading the same character over and over again. What we're doing is providing a locking protocol that says, type a key. Once you've transferred the data, well, actually, as soon as you type a key, it immediately locks the keypad. It then transfers the data into the port and then turns on the ready bit. Somebody looking for the ready bit will eventually see it. They can read the input port one time, but then they must go down and write the acknowledge bit. When they write it, they just have to write it as a 1. The port will take care of giving you one of these. We just write it as a 1. If you were to read it back, which we can't do, by the way, but if we were, we'd see that it had gone on and off. This signal is also mirrored up here. As soon as it sees that signal, it turns off the ready bit. Then it re-enables the keypad. Now, you need to have that protocol pretty much memorized to be able to write code that's going to be able to do what we just said. But that's the way the inputs and the outputs work on this machine. Primarily, we have a 16-key keypad. Our answers will be displayed in 8 LEDs, which are strung out like a binary display. And we have that special protocol that we use in order to cause data to be readable and predictable that we've got a valid byte. Now, there's one peculiar thing about these when we're using the instructions. That is, when we talk about them, we talk about the input ports being port 1 and port 2. The output ports are port 3 and port 4. Do you remember back when we were looking at the instruction sheet, I said, by the way, these all are direct memory access. They turn out they're direct memory access, but to what we would call I/O memory. It's a separate set of memory used just for the input-output. It turns out we have 256 bytes that we could use for either input, output, or both. And we also don't have to use them all. In our case, we're only using 4 bytes. But on the chart here, when they talk about input port 1, they're actually talking about memory address or I/O address 00. This is I/O address 01. This is output port address 02. And this is output port 03. So when we encode it in an instruction, we'll have to use these numbers. But when we talk about it, we could talk about it being the first output port or output port 3, second output port or output port 4, which is encoded as output 03 in the instruction. Anybody have any questions about input or output ports at the moment? Now, a reasonable thing to do is to know what these instructions are without having to look to see if such an instruction exists. For example, let's assume that somebody asks us to write a program that could read a byte of memory from the RAM and return, let's just say return or compute its 2's complement. Okay, now a couple things. First of all, in the last problem we did, up here where we put things at 8,000, we're putting this data into random access memory. That means this is the way it looks while the program is running. But these addresses would not be, or that data would not be saved across a power on. So a realistic writing of this code would have moved this back into ROM. This one, however, we kept all our data in the place where programs are going to get loaded. So we didn't need anything in ROM. The one we just used said, we're going to read something out of RAM, which is in the area past 8,000. We don't know how it got there, but it's there, and 2's complemented. So what instructions would I use in order to do a 2's complement? So I'm going to go back, and if you guys got the 2's complement right on your exam, I'm going to mark it wrong because you don't know how to do it. It sounds like looking it up on a calculator to me. Don't give me more than 2 people that can do a 2's complement. Okay, Scott, what would you use as your instructions?
We could start with the CMA to take the ones complement. Oh, do we have to load the accumulator first, actually?
We'd have to load the accumulator first, sure. Okay, so we're going to load the accumulator. And we said in ROM, it might be at 8,000. We don't know. It's somewhere in memory. Okay. Now it's in the accumulator. What are we going to do? You said complement the accumulator?
Yeah, that's our first step to take the ones complement.
And what's the second?
We need to add 1 to that so we can move MVI.
Let's do something easier than that. This is one of the reasons why once you've been through and learned your instruction set,
Yeah, so we
this will
can
just kind of jump out at you.
we can INR A.
Okay, and halt. You proud of your program?
Sure.
You should be. I mean, that's good. We load the equipment. Now, time-wise, this is actually pretty good, right? Okay, that's going to take 4. That's going to take 4, 5. That's not many. We have to get it out of memory somehow because we said it's in memory. We didn't say it was in an instruction. If it were in an instruction, it's even easier, right? We go load immediate. Right? No, on this machine, it's move immediate, I'm sure. Into the accumulator, the byte we wanted to change. Problem with this is, if we know this, when we're writing the program, we also know the answer. Right? If we already knew it. So any smart compiler would throw some of these instructions away and just simply put the 2's complement in the accumulator. So it probably was more likely that we would have done a load accumulator, from wherever we had our data stored. Robert, you have a comment? Okay, make sure you're familiar with these so I don't have to keep reviewing what they are and how they do it. And make sure you have looked very carefully at that protocol for reading the keys. What I'm going to do on Wednesday is I'm going to give you an emulator, which is really an SAP2 in software. We're going to write some programs. And, you got to get the code right in order for your program to work. And we'll be able to encode, decode some things, see how long they take, the timing. Should be fun. I mean, if you don't like doing this, I don't know why you have ever went out and bought a compiler except for maybe to use YouTube or something. Or a computer. Not necessary if you're not going to be a computer scientist. And this is high computer science we're working on now. Anybody have any comments? Now, I've had classes where people came and their eyes were rolling back in their head after this first lecture on the SAP2. If you spend a little time looking at it and think about it, this is incredibly simple stuff. It's just very, very detailed stuff. So you want to make sure you really, really get into it, pay attention to it, and don't get frustrated with it so that you can move ahead. We've got bigger fish to fry than this one. And we're only going to stick on the SAP2 for a little more than one more session. So make sure you're really doing, and go back and review the SAP1 if you can't remember how something works. If I were to ask you, given, where'd I put my machine? I've lost it. Probably have it in Paint or something now. If I said, using this chart, tell me what signals have to happen in order for you to do a logical AND instruction, you'd have to be able to tell me what control signals you did. It works exactly like the SAP1. We already know, we know this guy's going to have a LT and he's for load the T register. He's going to have an ET to enable him to write. He's got to have an edge triggered clock. This guy's he's a little different, but we can see how he operates. Review that. Make sure you're not reading notes or listening to recordings or something like that. That's why these aren't lectures. They're do it and learn it as we do it. Don't wait till tomorrow to learn it. Learn it as we go. Okay, I think we've run over time by a little bit, so I guess on the next exam, I'll just make the exam 2 minutes shorter. So you all have a nice time until next then. And for homework, really, really become available. Try to write a little program that does something. Take an uppercase letter, turn it to a lowercase letter in code, and vice versa. You know how to do that. You know how to convert to ASCII. And I'll see you then. Everybody tell me good night and enjoy your evening.
Night, Professor.
Bye-bye.
Professor.
Have a good night,
Bye-bye.
Professor.
Good night, Professor.
Good night, Professor.